Okay, in the second half of this section, we're going to look at applications, or how we're going to apply using the standard deviation and or variance in some calculations here. The first of which is the coefficient of variation. Then we'll have Chebyshev's theorem and something called the empirical rule or the normal distribution curve. And each of these are going to measure or do different things with a standard deviation, but they're going to use those to make some calculations or comparisons. So our coefficient of variation is where we'll start. It is used to compare the spread or the variations of two different sets of data. You can see right here our coefficient of variation symbols. This is our sample standard deviation. This is our sample mean multiplied by 100%. So it's our standard deviation divided by our mean multiplied by 100%. Population is the same calculation. It's a standard deviation divided by the mean multiplied by 100%. Just notice the different symbols. For our sample values, we use letters out of the alphabet. For the population values, we use Greek letters from the Greek alphabet as far as those symbols are concerned. Either way, our coefficient of variation is the standard deviation divided by the mean multiplied by 100%. And once again, that allows us to compare how spread out two separate sets of data are. So I could take my test scores from a stats class and compare the variation of the test scores in a trig class and know which ones were more spread out compared to the mean itself. Chebyshev's theorem is a theorem that uses a standard deviation to tell us what percent of data will fall within a given range. So let's say the mean on our last stats test was I'll just say a raw score of 54. I might want to find out what percent of the scores are going to fall between, say 39, 39, impossible, 39 and 69. Okay, so I would use Chebyshev's theorem. Chebyshev's theorem says that percent is 1 minus 1 over k squared. You can see that written here. I'm going to write an equation that equals the percent of values that fall between there. The key here that k is a number of standard deviations. So how many standard deviations are we above or below that mean? That's what k is. It's a number of standard deviations, and we use that then to calculate what percent are going to fall between these two values of 39 and 69. And then the empirical rule measures essentially the same thing, just in a different format. The empirical rule, again, is also called the normal distribution, or you might see it referred to as a bell-shaped curve. If I can squeeze this in, I don't know if I can squeeze it here in the bottom or not. I'm going to try a bell-shaped curve. It's going to look something like that. The mean goes right down the middle, so our mean goes here. If I go down 1 standard deviation, so our mean minus 1 standard deviation, or I go up 1 standard deviation, that's where 68% of the values are going to lie. That's one of the numbers we're just going to have to basically memorize or know. 68%. If I go down another standard deviation, so I go down 2 standard deviations, or I go up 2 standard deviations, then we have 95% according to the normal distribution curve. And there's one more number. If we go down a 3rd standard deviation or go up a 3rd standard deviation, then between those two numbers we have 99.7% of the values will fall. So 99.7. So you can see those listed up here: 68% within 1, 95% within 2, and 99.7% within 3. And that will be the work here in the second section, working with the coefficient of variation, working with Chebyshev's theorem, and working with the empirical rule or the normal distribution curve. So we'll jump into some examples of each one. First one you can see here says the mean number of sales of cars over a 3-month period is 87, with a standard deviation of 5. The mean of the commissions is 5,225. The standard deviation is 773. Compare the variations of the two. To compare, we use that coefficient of variation. So I'm going to write that down again. It's our standard deviation divided by our mean multiplied by 100%. So in this case, we have one for the number of cars being sold. So that coefficient of variation is going to be our standard deviation of 5. The average number of cars sold is 87, multiplied by 100 to make it a percent, and that percent is 5.75%. So that's the number of cars sold. We then can calculate a coefficient of variation for the dollar amounts over here. That's going to be equal to our standard deviation, which is 773, divided by our mean, which is 5,225, multiplied by 100 to make it a percent, and that percent is 14.8%. So what that tells us, 14.8 is obviously larger than 5.75, so our commissions are more spread out. Okay, one employee or one salesman might have made $3,000 in commission. Another one might have made $15,000 in commission. They're more spread out because this coefficient of variation is larger, where most of our salesmen are all pretty closely grouped around 87 sales per month. Not going to go too far away from that because 5.75 is our coefficient of variation. They're considerably smaller than the previous one. See that one more time. Mean number of pages of sample women's fitness magazines is 132 with a variance of 23. The mean for the number of advertisements of a sample women's fitness magazines is 182 with a variance of 62. Compare the variations. Once again, a comparison is that coefficient of variation. I'll write that up here again. Standard deviation divided by the mean multiplied by 100%. So for our number of pages, our variance is 23. We established in the previous section the standard deviation is the square root of the variance. So to get the standard deviation from my formula, the S, I take the square root of 23, divide it by my mean of 132, and multiply it by 100 to make it a percent. And my coefficient of variation for the number of pages is about 3.6%. I'm going to repeat the process for the number of advertisements. Notice the variance there is 62, so my coefficient of variation there for the advertisements is the square root of 62. That makes the variance the standard deviation, divided by 182, and multiplied by 100 to make it a percent. In this case, we get 4.33%. You can see these are a lot more closely grouped, 3.6 and 4.3, but 4.3 is larger than 3.6, so there's more variation in the number of advertisements than there is in the number of pages. Okay, so there's two examples on our coefficient of variation. From here, our data set has a mean of 212 and a standard deviation of 18. What percent of the values will fall between 185 and 239? Since it doesn't say anything about being normally distributed, we use Chebyshev's theorem. So my mean is 212. I want to find what percent fall between 185 and 239. So if I go from 212 down to 185, that's a distance of 27. If I go from 212 up to 239, that's also a distance of 27. What I want to do next is convert that distance to a number of standard deviations. So that distance is 27. From up here, my standard deviation is 18. So I'm going to divide this by 18. In other words, 185 and 239 are 1.5 standard deviations away from the mean. That number of standard deviations is our K in Chebyshev's theorem. So to calculate our percent, we take 1 minus 1 over K squared, which we just found K to be 1.5 squared. And 1 minus 1 over 1.5 squared tells us about 55.56% of the values are going to fall between 185 and 239. Again, this is according to Chebyshev's theorem. So basically 56% of the values are going to fall between 185 and 239 based on that calculation. We'll see that a second time here for a data set with a mean of 1850 and a standard deviation of 72. What percent of the values will fall between 1698.8 and 2001.2? I'm going to set up the same little tree diagram. 1698.8, 2001.2. If I find the distance from here to here, it's 151.2, and from here to here is also 151.2. We want to convert that distance over to a number of standard deviations, so I'll take that 151.2 and divide it by my standard deviation, which you can see up here is 72. That tells me it is 2.1 standard deviations away. That number of standard deviations we are away is k, so 1 minus 1 over 2.1 squared will tell us that 77% approximately of the values will fall between 1698.8 and 2001.2. So there's our first look at Chebyshev's theorem. Let's move on and continue with Chebyshev's theorem, but we have a different look here. 80% of the values will fall between what two numbers for a data set with a mean of 105 and a standard deviation of 12. So notice we have our mean, but we don't know what number we go down to, and we don't know what number we're going up to, but we do know that between those two numbers is 80%. Essentially what we're doing here is working backwards. We have our formula 1 minus 1 over k squared. We said earlier today that equals a percentage. Well, the percentage is 80%. So I'm going to use this equation to work backwards and find my k. Once I found k, I can multiply it by my standard deviation and add and subtract it from 105. So I'm going to go through the step-by-step process to revisit our algebra here. First thing I would do is subtract 1 from both sides, so negative 1 over k squared equals negative 0.2. Since both sides are negative, I'm going to multiply both sides by a negative 1 and make both sides positive, just to make things easier to work with. Right after that, I'm going to multiply both sides by k squared. That way I can get rid of my fraction over here. 1 now equals 0.2 k squared. I'm trying to solve for k, so I'm going to divide by 0.2. And k squared, k, Jiminy Christmas, k squared now equals 5. If I take the square root of both sides, k is going to equal about 2.24. Square root of 5 is 2.24. So once again, repeating what we've already talked about, k is our number of standard deviations. So up here, I'm going to take that 2.24 times my standard deviation of 12, and that will tell me how far to move above and below 105. If I multiply that, I get 26.88. So I take 105 and subtract 26.88 to get my lower limit, which is 78.12. And I take 105 and I add the 26.88, how far we want to be away, and that's 131.88. In other words, 80% of the values are going to fall between 78.12 and 131.88. Let's try that process again. Mean of 2376, standard deviation of 172. 90% of the data will fall between what two numbers? Set up the same way. 2376 is my mean. I don't know what my lower limit is or my upper limit. I just know that 90% fall between those two. Okay, so we go over here and we'll say 1 minus 1 over k squared equals that percentage of 0.9. So I'm going to zip through this a little bit quicker this time. 1 over k squared equals 0.1 when I subtract 1 from both sides. 0.1 k squared equals 1. K squared equals 10. And k equals about 3.16. So 3.16 is our K, how far we are away, or how many standard deviations we are away. To find out how far, we take 3.16 times the standard deviation of 172, and that gets me 543.9. That's how far I want to be away from 2376. So I take 2376 and subtract 543.9, and I get 1832.1. And I take 2376 and I add 543.9, and that gets me 2919.9. In other words, 90% of value is going to fall between those two numbers according to Chebyshev's theorem. Now notice the difference between the last four problems and these next two. In a normally distributed group, so there's our big difference, normal distribution, that's that curve that we had up here earlier. So I'm just going to re-sketch that, and we'll plug in the information from the problem. Normal distributed group, 95% will fall between what two numbers if our mean is 18 and our standard deviation is 5. So our mean cuts this curve in half. In other words, 18, 50% of the values lie below 18, and 50% of the values lie above 18. If I go one standard deviation away, so I go 18 plus 5, or to 23, or I go 18 minus 5, down one standard deviation to 13, 68% are going to fall between those two numbers. There's the first percentage we need to know. 13 and 23, 68%. One standard deviation away. We've gone up 5 and down 5. If I go a second standard deviation away, 13 minus 5 is 8, or up another standard deviation, 23 plus 5 is 28, there is where 95% will lie. That's what's being asked in the question. So what two values? That would be 8 and 28. Between 8 and 28 will include 95% according to the normal distribution curve. We have a second example of that here. Again, notice the phrasing in a normally distributed group. So I'm going to start the same way and sketch that curve, putting our mean right down the middle. In this case, our mean is 35. And then plugging in our percentages. If I go up one standard deviation, my standard deviation is 6, so 35 plus 6 is 41. Or down one standard deviation, 35 minus 6 is 29. That's where we have 68% within one standard deviation. We'll go down another standard deviation, so 29 minus 6 is 23. Or up another standard deviation, 41 plus 6 is 47. Between those two numbers, we have 95%. This time we're being asked for 99.7%. So I go down another standard deviation. That gets me down to 17, 23 minus 6, or up to 53, 47 plus 6. And within 3 standard deviations, or 17 and 53, is where 99.7% of the data values will lie. So there's a look at our normal distribution curve. We looked at Chebyshev's theorem, and we looked at the coefficient of variation to compare the spread of two numbers.